Okay, welcome, ladies and gentlemen. My name is Mark Billinghurst, and I'm here from the Auckland Bioengineering Institute. Normally, Peter Hunter, who's the director of the Institute, would be welcoming you all, but he's away attending a very important event at the Royal Society of New Zealand, where one of our faculty are being inducted into the Royal Society. So you've got me for tonight. And this is the first of what I think is going to be an ongoing series of special guest speaker talks from the Auckland Bioengineering Institute. So what I'm going to do is talk about the Institute for a few minutes, talk a little bit about my own work in the Institute, and then I'm going to introduce Aaron, who's our guest of honour tonight, who's going to talk about his work most of the time. So I think many of you will know the Bioengineering Institute. It's one of the largest research institutes here at the University of Auckland. And as it says here, the purpose is really to create world-leading research that will improve medical diagnosis and the treatment of injury and disease. There are many, many different principal investigators inside the Institute. Over 300 people are part of the Institute, so it's a lot of very diverse research going on. And it's really, they try to achieve this goal through the application of engineering science and technical innovation to medicine and human physiology. So there's a number of strengths with the Institute. There's a number of world-class researchers working with very advanced facilities. We have a number of research postgraduate degrees, masters and PhD students who have a very good master's program in bioengineering, and a lot of international collaborations. In fact, Peter Hunter, our director, has a joint appointment with the University of Oxford, so he spends time here as well. There's also a strong focus on commercial development and a number of spin-out companies. I'll talk about that more in a minute. And in terms of the research, we also host the New Zealand MedTech Core, which links researchers throughout New Zealand and industry with a medical theme as well. So this is one of the largest research collaborations in New Zealand around medical technology. Here are some of the key areas of research that happens in the Bioengineering Institute. There's a lot of work on medical devices, including biorobotics, soft tissue mechanics, imaging, bioinstrumentation. There's work on biomimetics, so trying to build devices that mimic natural organs or anatomy. And also augmented human technologies, which is where my group is. There's also a group doing work on assistive augmentation and artificial intelligence. We also do engineering for clinical technologies, such as women's health, eye health and surgical engineering, and then also computational experimental physiology. So one of the first projects that was very famous was the work on building a mathematical model of the human heart and using that model to simulate various problems with the heart. There's a very strong device instrumentation group, including building technology that is implantable or embeddable and providing wireless power to that technology. We also, through the biomimetics and human augmentation, we've done work with artificial intelligence. One of the projects that we're very well known for and is famous for is the Soul Machines, which is one of our spin-out companies. So Soul Machines is a company that spun out from the work of Mark Sagar in the lab in the Institute, and it's developing one of the most intelligent artificial characters you can interact with. And so this is
I'm really pleased to have helped so many people, but I've only just started my banking journey. I still have so much to learn.
We can't believe that it's been 3 months since we launched Jamie, and we're really pleased with how she's going. I think customers generally are loving her. She's had well over 12,000 customer conversations.
Lots of people ask me how to open an account.
She's an evolving piece of work, and so by putting her out into the world, we're able to find out how people are responding to her and what they think.
Sorry about the audio going up and down a bit.
Yeah.
Hi Jamie, how can I get a new credit card?
I can help you order a new credit card.
As soon as the Jamie technology was available, there was an expectation that she would be able to answer real-time questions about most topics, and so we're actually doing a lot of work to build in the ability for her to answer real-time things, such as what the FX rates are or interest rates.
Yeah.
This would work a lot more closely to the way people are actually asking us questions. Mm-hmm. I think what we're hearing from the public is we want her to be able to do our banking for us. We want her to be able to give us much more comprehensive answers.
Thanks for asking.
And for us, that's the exciting next step.
I need to open a new savings account. Would you be able to help me with that?
To make her much more helpful and much more...
So I'll stop it there. So that's Jamie. That's one of the virtual characters produced by Soul Machines. If you want to try her out, you can go to the ANZ bank website, anz.co.nz, and you can interact with Jamie through the web browser, and you can ask her questions like how do I open a bank account and so forth. So Jamie looks very realistic and very beautiful, but the actual core piece of technology is all the artificial intelligence behind that. And so the team have basically simulated a human mind and create the ability to have a quite realistic dialogue with a virtual character. So that's an example of technology from the lab that's now been commercialized. Soul Machine has over 80 people working for them, and they've received, I think it's $25 or $30 million of venture funding now, so it's quite a big success story. Of course, we also, as I said before, strive to look at improvements in women's health, and so we're doing things like pregnancy and childbirth. We're doing work on advances in medical imagery, biomedical informatics, and surgical engineering. And so we're trying to look at how we can apply that medical data to improve women's health as well. And we have a strong group in computational and experimental physiology. You can see this is Miran Tafai's work on simulating the lung and building mathematical models of the lung. And we've also done the heart and other organs. So we're looking at trying to build a mathematical model of the whole body and being able to use that to predict impact of medicine and so forth on the physiology. So that's the Bioengineering Institute. If you're interested in finding out more, you can contact us here. And we're just up the street at number 70 Simons Street. So I want to talk now briefly about my piece of the Bioengineering Institute. I've only been here for 6 months, so I'm a relatively new professor. And when I came here, I brought some people with me and created a new lab called the Empathic Computing Lab. So for the next couple of minutes, I'll talk about that. This is a joint lab between the University of Auckland and the Bioengineering Institute and the University of South Australia. So I want you to imagine for a minute that you're watching the Olympics in Tokyo in 2020, and there's a cycling event. It's the mountain biking, and you're at home on couch watching the mountain biking on TV. Now, normally you'd see the mountain biker from an external camera, and you'd watch them as they hurtle down the track and around the corners and so forth. But wouldn't it be much better if you could sit at home and have the feeling of being in the mountain bike seat and being in the race itself? So instead of looking at it from externally, you could have this view here. And using some device, you'd be able to look through the eyes of the mountain biker and understand what's going on and the excitement of racing in that event. So that's kind of what we're trying to do with our lab here. It turns out there's technology already that allows you to share a viewpoint like this. So for example, in my hand here, I have the Google Glass display that came out in 2013. It's basically a small computer you wear on your side of your head and just looks like a regular pair of glasses. But the interesting thing is it has a small camera on it. And with this camera, and combined with some processing and display, we can stream the video live to a remote person. So indeed, I could ride the mountain bike in the Olympics and wear this device, and somebody at home could watch the video of that event. And so people have used that. For example, there's a boy going to the vet, and the vet is, or a boy not going to the vet, but the vet is holding up a python, and he's able to stream video of that to this remote boy. Or here's a doctor performing a surgery, and he's streaming video to some medical students so they can see through his eyes what they're doing. So it's fantastic technology, but there are some problems. So one of the problems is that if I'm streaming video from here, the remote people can only see where I'm looking. They can't look around and see everything else. They can't get feedback. You know, if I'm the doctor doing the surgery, the student can't point at something and say, what's that thing over there? So in our lab, we're looking at how we can get over that and create a stronger sense of connection. And the reason for doing this is there's several technology trends happening right now. So one is towards improved content capture, to move from, you know, we all use Skype or Zoom to do video conferencing, see each other's faces. But now you've got technology where you can live stream camera views and you can share a view of a real world or share spaces. There's much better network bandwidth, which means we can have high definition video conferencing and share really rich communication cues. And most interestingly, we've got technology where computers can look at us with cameras or listen to us through microphones and recognize, to some extent, our emotion and recognize our behavior. So these trends together, natural collaboration, experience capture, and implicit understanding, in our lab, we're working at the junction of that in an area that we call empathic computing. So most of you probably know what empathy is, of course. Alfred Adler famously said empathy is listening, seeing with the eyes of another, listening with the ears of another, feeling with the heart of another. And what we want to do in our lab is answer this question. Can we develop systems that allow us to share what we're seeing, hearing, and feeling with others? So already with things like Google Glass, you can see what I'm seeing and hearing, but we want to focus on the feeling as well. Can you get some idea of what I'm feeling and what I'm going through at a particular point in time? So I'm going to show you a couple of research projects that do that, not just to touch on them, and then I'll talk about how you can engage with us a bit further if you want to. So we're doing some example projects. We're mostly working on using technology like wearable devices or augmented reality or virtual reality or using physiological sensors to be able to measure your heart rate or your emotion. So a couple of projects. You've got watches now that allow you to measure your heart rate or some other physiological sensors. And so we can basically use that to build some sort of emotional dashboard or share that raw data with devices that will know what emotions you're feeling. So a couple of years ago, we built a system called the Empathy Glasses. And it combines three technologies together. First of all, eye tracking. Secondly, augmented reality glasses. And a special pair of glasses called effective wear glasses. So you can get software now that looks at a camera and uses the camera looking at your face to understand what your emotion is. So if I smile at the camera, and to some extent that's what virtual characters like Jamie do. They look through the camera, look at your face, and they know whether you're smiling or unhappy or whatever else. But if I'm building a wearable system, I can't really use that because I can't put the camera on a stick and walk around as I'm looking at my face. So what we did in this case is with these special glasses, the effective wear glasses, have photosensors that measure the distance to your skin. And as you make different face expressions, your muscles move, and we can detect that, and we can then know what emotion you're showing. So the most important reason for combining these three together is that we want to be able to share the same implicit cues that we have in face-to-face communication. So when I'm talking to you face-to-face, I can look at your face expression, I can make gaze, I can understand non-verbal communication. So we combine them two together, and then this is an example of the system being used. You can see on the guy's wrist is the heart rate sensor I was talking about before. This is all the technology he wears, and on the right-hand side is what he's seeing. So we take a live video from the camera, send it to a remote person, and the remote person now can send feedback. So there's a green dot you can barely see there, and that's the mouse pointer from the remote person saying, looking at this thing. And then most importantly though, the red dot is his eye gaze. So many of us have done video conferencing, but sometimes we have the video conferencing camera and we're not sure exactly where the remote person is looking. But with this eye tracking system, we know exactly where you're looking. And that's important because before we pick up objects or move them, we always look at them. So using that system, I'll just turn this down. Oh, that's annoying. So, so here's a remote person helping him, and you can see he's moving around the green dot. And when the person's paying attention, the red dot follows the green dot. And so he's telling him to move that block over here, and you can see the dots are moving around. Now you can imagine, this is obviously a very simple task, but if he was doing something like bomb disposal, and I'm about to cut the wrong wire, and the guy knows because I'm looking at that wire and he says, don't cut that, so now I can know what he's doing. So this is an example of how we can use empathic computing technology to be able to share some of the same cues we have in face-to-face communication. And we did a little user study, and we showed that indeed by sharing the gaze cue, that people feel like they're more connected because they know where the other person's looking, when they're effectively looking through their eyes. But there's one problem with this, and that is that just like the Google Glass, the person can only look in the direction that you're looking. So we did a second project, which we call the ShareSphere project, where we stream a 360 video from one person to a remote person, and the remote person is inside a VR headset. And then in the VR headset, they can look around in their space. And we also have the VR person has a special technology to capture their hand gesture. And so I can make gestures in space, and this person's wearing an augmented reality display, so he'll see these ghost hands floating in front of him. And he can use that to help guide and perform certain tasks. So here's a video of that working. This is a project done with a power company, and the reason why they wanted to use this is to provide a remote assistance. So here's a person standing in front of a very complicated power control system. He's wearing an augmented reality display, the 360 camera, and he's streaming video to a remote person who's going to help him. And this is what he sees. He sees that there's ghost hands. He sees the remote person pointing in the real world, and then being able to look around. And that green square shows him where the remote person's looking, because now you've got a 360 video, the person can look in any direction they want, not in the same direction as you necessarily. So here's the remote person. We've got live video coming in, and he feels like he's standing in the power station, because wherever he looks, he sees the power station. And now he's able to use his real hands to interact and draw onto the real world and help the person perform the task. So this is very important because remote assistance is a very important application area. The power company told us an example of where they had a technician make a mistake, and it took a power generator offline for an hour, and it took them an hour to drive somebody out there to fix the problem. And when the power generator was taken offline for an hour, they were fined $500,000 because 1,000 homes lost connectivity. And the person who was on site didn't know how to fix it, and it took an hour for the person to get there to fix it. So with our technology, they would be able to fix it very instantly. But there's one problem with this one, and that's the 360 video, but it's not like sharing the same 3D space because it's a video. And so the final project I want to show you is work we're doing on augmented reality to virtual reality collaboration. The basic idea is that in the future, we should have some technology where you can walk into a space, hold up a camera, and it'll capture a whole 3D model of the space. It's not a picture, but a 3D model. And then we can send that 3D model to a remote person, and then the remote person could be in VR and walk through the 3D model. And then you have a collaboration between a real person and a person in VR. And so in this case, the person who's in the real world will have the AR headset on, and they will see beside them a virtual ghost character of the person who's helping them remotely. So one example of how that might be used, you know, you can imagine the Christchurch earthquake that happened 8 years ago now. If you want to send somebody into a building that's been damaged by the earthquake, they might send a first responder inside, but the police chief or fire chief outside the building might want to help that person. And so if the person goes into the building with this magic 3D scanner, they can scan the 3D building, send it out, and the fire chief in the VR headset could feel like they're in the building with them, helping them, and when I'm in the building, I'll see this virtual character beside me say, look over there or move over here. So this provides a much higher degree of presence. And just to show a video of that, so here's our lab. This is a virtual copy of our lab on the right, and when you put the AR headset on, you can see the other person in pink. These green lines out of his face show where they're looking. So normally in a face-to-face situation, I only know where you're looking when I look at your face. But in virtual reality, we can draw a view frustum or a view cone that shows where you're looking. So I now know where you're looking without even looking at your face. So you'll see that here. So those pink lines show where the person next to me is looking. And we've got some virtual hands floating around. And so now we can collaborate together. There's my friend right there working close beside me. So in this case, they're doing some sort of remote task where they've got to manipulate blocks around. Now the final thing I want to mention is that now we've got this collaboration between AR and VR. You can do some things you can't do in the real world. So for example, because the person in virtual reality is a digital person, I could make their body really big or really small, and now we can collaborate at different scales. And that's what this video here shows. So here we are in the living room together. There's my friend. We're putting objects in the living room for some reason. And now I'm going to make myself much bigger. So again, if I was the fire chief and I'd sent 5 people into the building, maybe I want to make myself really big so I have kind of a God's eye perspective and I can see all the building people at the same time. Or maybe I want to make myself really small so I can search parts of the building where the regular people can't go. So you'll see that in a minute where he changes his body scale down really small. And you can see the person on the little window there walking around in the real world in augmented reality, and she's seeing on the window above that her friend in the real world. Now he's shrunk himself down really small, or 1-to-1 scale now, and then really small. And you'll see little mini head there, and he looks up and he sees the giant head of his friend walking together. So by using virtual reality, you can do some types of collaboration you can't do in the real world. So just to wrap up, you know, we're doing some interesting things with AR and VR for empathic computing. VR systems are really good for sharing experiences and providing total immersion experiences, changing your body scale. Augmented reality is ideal for live sharing and providing remote assistance in the real world. But this kind of feeds into broader technology trends. So there's trends now with advanced display technology where you've got VR displays that have very big views. You've got technology where you can capture scenes. You can use natural hand gestures to interact. You've got eye tracking technology. And just recently, people have started to release devices with emotion sensing built into them. So for example, 2 weeks ago, we got the special headset from Korea, and it's a VR headset. But on this side, if you've got very good eyes, you'll see these little gold-colored dots. These gold dots are EEG electrodes. So when I wear this, it can measure my brain activity in the front of my head. And there's also eye tracking here as well. So if I'm doing something and getting confused, this headset will detect that level of confusion. So now what we're really interested in doing is combining these all together. And we've most recently done a project, or just starting a project on brain synchronization. So it turns out when you sit together with somebody and do the same task, so if I put my finger in the space and move my hand around and you track my finger with your finger, then sometimes our brains synchronize and the alpha waves start pulsing at the same frequency. And when that happens, you kind of feel like you're entering into a flow state or a state where you're really connected with the other person. It's only a phenomenon that's been studied over the last 10 years because previously the EEG equipment was super expensive, so you wouldn't necessarily be able to have two devices doing that. But recently the equipment cost has dropped down, and we've got ourselves, this is actually an open source EEG, so it looks a bit duct taped together, but unlike this one over here, this one, these blue guys right here, they're all the EEG sensors, and we have 16 that covers the whole head. And so you can see, this is just an experiment done last week actually, so you can see my two students pointing fingers at each other and waving their hands around, and we want to see if we can now measure the brain synchronization, and then more interestingly, do the same thing in virtual reality, and we'll see if we can make the virtual reality experience synchronize yourself much quicker. So you can imagine you're doing a task in VR with another person, but because virtual reality, we can take your view and put you inside the other person's body. So now you're both looking through the same pair of eyes, and I see my hands come out of your body, and we can work together. And the theory is that by inhabiting somebody else's body, our brains will synchronize even faster. And nobody's done that before, so it's a brand new experiment. We're very excited about that. And here's our initial results. Looks very fancy. But basically, if you look at the red line there, this is the amount of brain activity happening. And you can see on the red line, we've got this a lot of brain activity happening on the upper right-hand side of one person's head, and that maps onto the upper right-hand side of the other person's head. So indeed, just by doing this finger tracking task, those two parts of the brain are starting to synchronize with each other, but very early days. So all those technology trends together map to create something called Empathic Tele-Existence. And the idea is you can use technology like this to move from an observer of somebody else to a participant with them in an activity, to change communication from explicit to implicit communication, and to really have an experiential collaboration where you start feeling like you're doing things together. So it's a very exciting time to be doing this type of research. So we'd love to collaborate with some of you. We are doing industry-related projects, so if you're from a company, we'd love to work with you. If you're a student or an academic, we'd love to work with you, and we've got money to work with you as well. So that's all really great. And most immediately, if you like the things you're seeing here, and Aaron's going to talk about some more things that might be interesting to you, then on Friday this week, so this Friday, we have a demonstration evening. And Aaron's going to show you, he's got this very special headset on, of which there are very few of them in New Zealand. And if you come on Friday, just down the street, just the next building actually, to the architecture building, between 4 and 6:30, you can try 9 different augmented reality demonstrations that my students are doing. So we have a summer school running right now for augmented reality. For those of you who are in the summer school, can you put your hands up? So you can look around, you see a great audience. They've done some fantastic demonstrations, nearly 50 people. There's a demonstration where you can throw penguins at a box of ice, where you've got to herd cats, which everybody loves, of course. You've got laser eyes, and you've got laser beams coming out of your eyes and shooting things, and lots of other stuff. So it's going to be fantastic. So on Friday, if you're not doing anything in those times, please come and see. We're just right there. So that's me. I'd love to talk to you more, but I'm just a warm-up act. So if you want to talk to me more, there's how you contact me. And I'd like to now introduce Aaron, who you're really here to see. So Aaron is an old friend of mine. Well, he's not old. We've been friends for a long time. And
he's getting old.
Yes, he's getting old. So Aaron's an ACM Distinguished Speaker, which means the ACM, which is the Association of Computing Machinery in the US, paid for him to come to New Zealand to speak to you, so we're very lucky. He's the Chair of Human-Computer Interaction and the Director of Impact at the School of Computer Science at the University of St Andrews. Most of you know St Andrews for the golf course, but it turns out St Andrews has an amazing university, especially in human-computer interaction. And Aaron does amazing research in a number of fields, in global HCI, so how you can apply human-computer interaction to a wide range of different countries. Discrete computing is what you're going to talk about today, so what happens when computers disappear and how you can interact with them. Information visualization, novel on-body interaction, and pervasive and ubiquitous computing. And he's also the ACM SIG-Chi Vice President of Conferences, so he's very, very important in this organization and helps conferences getting started. So we're very lucky to have him. So I'd like to turn the time over to him. Do you want me to plug you in, Aaron, or how's he going to do it? Look at. And he's going to talk for about 45 minutes or so, and then we'll have questions at the end of that time. So you're all set? Great. Oh,
Let's see if we get a
it's
signal.
almost there. It's one screen, two screens. Excellent. So let's
Very good.
welcome Aaron.
Thank you very much.
Thanks, Aaron. And take it away.
Okay, thank you very much, Mark. Thank you. So it's my great honor to come here.
Oh, Aaron, did you want a microphone? Or?
I can speak loudly, but I'll
You've
probably
got a
put on a
great-
microphone once I
sure.
get out of my other things. I'll put it on a second. Oh yeah, here we go. Okay, yeah, so as Mark said, I'm a professor in the University of St Andrews in Scotland, but I'm actually currently a visitor in the National University of Singapore, which makes coming to New Zealand nice and close, relatively speaking, rather than coming to Scotland. Hello, hello. There we go. I'm going to hold it for now. Okay, so that's my website, and that's the research group that I head up. Although I'm no longer heading it up because we have somebody else who's the acting director while I'm away. So I'm going to talk to you about a way of thinking about computing that I describe as discrete computing, and we'll go through what that actually means as we get there. Now, first thing I have to do is I have to thank the ACM because they have a very nice program. They invite about 100 of their 100,000 members to join them as what are called distinguished speakers. And then we become available to anybody who's organizing an event like this, a summer school, another type of industry event. And then we get to come and talk about our research and just explain what is computing in its current form, like at the cutting edge and the research that we actually do. And the mission of the ACM, of course, is to kind of help computing professionals to magnify the reach of what they do, so that if you do some small innovation in your company and you're an ACM member, that through the ACM you could magnify the reach of what you do, so many, many more people would know about it. Because if you and your company know, that's good for you and your company. But what happens if this is actually a solution to a much, much bigger problem that could actually impact the lives of billions of people? So like rapidly get the technology out there. And the vision is really just to kind of get the knowledge and the skills and build the community and strengthen and share the community. So one of the programs they have is this Distinguished Speaker Program. So you can go to dsp.acm.org and there's more information about that. And there's about 100 speakers on very varying topics, from algorithms to distributed systems to cloud computing to Internet of Things, human-computer interaction, computer vision. Lots of, what's the term that they use? Renowned international thought leaders speaking on the most important topics in computing today. Since that includes me, that's slightly self-serving to read that out, but anyway. But the most important thing is that for a host organization or any organization, the ACM will provide the financial resources to enable the DSP speaker to come, and the local organization doesn't have to stump up, which is kind of important when we're thinking about HCI in a global context, when we're looking at the fact that, like I'm going to Colombia in August, I'll be going to North Korea at some stage to do a DSP, because local groups might not necessarily have the resources, but we have the energy and the drive to actually go to talk about our research beyond the borders. I also want to thank the Acute Centre for allowing me to come, because I'm a visitor there, and I'm not there, I'm here. And I would also just re-emphasize what Mark said. If you want to see the future, come along on Friday, okay? The students and the researchers and the developers and some people from companies and other academics in the university have spent the last 4 or 5 days putting together demos very quickly using new technologies, this empathic thinking of augmented reality plus sensing, to come up with new applications very quickly. So it's a real opportunity for you to come along and see that. So the Acute Centre, thankfully, has allowed me to come, and what they do is tangible interaction, augmented learning, and embodied experience. While I've been here, I've been like trying to understand what is the future, since you live in the furthest time zone, so you are the future. Every time the fireworks go off, we see Auckland, you're like, wow, it's already the next year, it's so advanced, okay? So I've been going out to actually explore your city in every single way. Not the Monzo way, if you don't know what that is, that's a yellow Monzo bike that somebody has really done a number on. It's like fundamentally destroyed. Like there's 8 pieces of that bike. So I've been going around running and hiking and zipping on these things and like nearly dying, just actually to kind of learn what your city is like and what makes it the future. Okay, I'm being slightly ironic and sarcastic here. It is the future, but it's the future to you. But is it going to be the future to other people? So what is discrete computing? What are we actually going to talk about with discrete computing? So as I stand here in front of you, and as I sat over there, and as I sat over there, I was watching you. You were watching Mark. And largely, even though I probably look a little strange, after a few minutes you just kind of ignored me. basically. I've worn this out around the city, not on a public scooter or anything like that, because that would be kind of dangerous in its current form. And I've only had one negative reaction, which was when I was paying a bill, the eye contact wasn't maintained. So I can see you, okay? So we're going to test this, okay? How many, put up a number of fingers. Okay, I think I see 2 fingers, is that correct? Okay, we'll do another independent, so you're not a plant. Okay, somebody else far away, right there, like, Jesus, okay, you've got a big hand with 5 fingers, that's good, I can see that. Anything else at the back? Can you lower it a bit? Bring it down, so bring it down. 3 fingers, yeah? Can you say yes loudly? Yes. Thank you, there we go. So I can see you, okay? But I am not in the same reality as you, okay? This is very important right now, okay? That's why I would encourage you to come on Friday to actually try this for yourself, because this unlocks your imagination and thinking. Okay, because right now you're all sitting here. Okay, and is that all that's here? Is anything else here? Like, do you think I see anything else different than you see? Yeah. One would hope so, given all this paraphernalia. What do I see? Okay, well, I was drawing over here. I see fish. I see plants. I see what do you call it? Coral. More coral over here. And down here, I see several very, very pissed off Tyrannosaurus rexes wandering around, and a whole set of, actually, let me just regain the head pose. Here we go, back. There's one there. So I'm just picking him up. So at my pointer, I now have a Tyrannosaurus rex flying in the air above my head. So, and this thing understands the space, okay? It understands that there's tables and there's people. It doesn't understand that there's people. It just understands surfaces. So I'm now going to put it right there between the 2 of you, and he's there. And he's now walking to the left, and he's walking across the table. He's getting a bit lost, and we'll leave him be. Okay, we'll find one more. And there's a fish, okay? With the fish right there on your head. And the fish is going away, and he's swimming away from you very elegantly. He's coming right back to me, actually. So he's coming to me, and he should know I'm here. Is he going to go through my head? Oh, he just disappeared. Clipping plane, okay? So that is a very important thing to me, because I've wanted something like this for the longest time, okay? Now, because I'm living in a deluded state. Now, what I'm going to do is, I'm going to do the following, and hopefully this works, because this is tricky. Now, you sit there and think, I can't see what you see. Can you not show me what you see? And the answer to that is, if it all works properly, maybe. Okay? So let me just unplug and plug in and see what we can see. And you'll know I'm not lying to you, because my head will be controlling what we see. Okay? Up there now. If that little dot on the far left goes green or yellow even to begin with. Okay, whoa, we're getting there. Okay, now I'm going to start the device, and if it goes green, you should have at least some sense of what I can see. But I'm not going to show you the fish. I'm not going to show you the Tyrannosaurus rex. I'm going to show you the research that I'm doing right now, and the reason I went jogging around your city is because I want to build a whole new way of experiencing that, so it's not just me. So let's have a look. So let's go over to Unity. Let's fire up Unity, and let's hope this works. And what you now should see on screen is what's wrong? What do you see? Wait. It's compiling. It's compiling. Give it a second. I'm going to look out. Okay, what you're about to see, if it compiles and loads and everything works. Oh, there we go. Okay. Okay, no, it didn't connect. Why did it not connect? Why did it not connect? Live demos are always a pain. Oh, there we go. Now, okay, look out. Oh God, it's gone. Oh no, this is confusing. I'm tethered here, okay? So there's no wireless connection, so you're gonna have to bear with me. Okay, I'm turning around. Okay, do you see all the people? Okay. And there's lots of them. And they're coming to me. And I've got them blocked away. Some of them are naked. And you know what? They're running around the room in front of you. I don't know what you're laughing about. And now they're coming towards me. And they understand the physics of the environment, you see? They get blocked. And they run away. What I want is, I just got out to your North Shore, and I decided to do a half marathon on the spur of the moment. And one day when I come back to Auckland, I'd like to rerun that half marathon, and I'd like to be at least as fast as I was when I was a younger man. And what I want is, I want the virtual me of today to be running ahead of the virtual me of tomorrow. And not just me, I want my friends and other people and the top leaderboards. And of course, I've got some like little buddies, this weird little dude here. Like, he's not running around. You see him? He's sitting right there, okay? But what I can do is, because this is a development environment, I can go and find one of them. And interactively, in real time, if I go down here, let's just pick something. Okay, so somebody tell me something so it doesn't look fake. Tell me something of a human, of a body character that you'd like to make 10 times bigger than it already is. Dear God. Oh, dear God. Okay, let's go for cheeks or head or something. Filthy imaginations in. Chin, head, arm. Let's go for arm. You will definitely see the arms. Okay, now let's go for, what else? Let's make their feet. Ears. Oh yeah, the ears are actually quite good. Where's the ear? Ear, here we go. Position, rotation, size. Okay. There's the ears. Now the ears are in a double. Okay, now let's look back. And let's see if we can find the poor character who's had their face ripped asunder. Where are they? Because they're just one of them. Okay. Do we see them? Do you see the arms? Okay, now, this is why I wish they were... Actually, I know what I'm going to do. I'm just going to let them run across behind me. Okay, let's just run. I'm just going to let them run out here. Okay, run here, run there. Oh, come on. Where are you? Run out, run out. Where's the army one? Oh, it's, you know what it is? You know what's wrong? It's stuck behind the wall. He's right there. He's there somewhere. He's stuck, but he's stuck behind the wall. You see? He can't get through the wall. He has to run around the wall. I have to move him and get him around the wall. Because it's physical, it makes sense. It's like, this isn't a virtual thing. If this was a rendering of a table in front of you, you wouldn't want to be able to run through the table. Okay, so you see him there with his big arms. And let's just do one last thing to him, and then we'll move off. Let's, legs. This is gonna, you'll definitely see this. Now he's short. Okay. And I can do this all day long. Oh, what's it doing? Okay, so you get the idea. Now, so I hope you understand that I'm looking out and seeing these people. So Mark promised me an audience of 500. So if I don't feel like I've got like value here for coming all the way to New Zealand, I can just go over here, copy, and now, there we go, more come in. And I can keep on adding them in. Oops, I can get the mouse in the right position. Where is it? What's it doing? There we go. And they're all running. Actually, the cutting and pasting sometimes breaks the models that you've actually got. Okay? Oh, my favorite part of this is actually if I press the letter C, watch this. Here comes all your politicians coming towards you. Okay? So that's what I'm working on this, but that's just one idea. Okay? Now I show this to you because I think it's kind of interesting with respect to discrete computing. Because if I had this and you didn't have this, you wouldn't know what I was seeing in the world. Okay? So I could do all kinds of things. I could see all kinds of information. So what is discrete computing? We're not talking about separate groups, okay? We're not talking about discrete as in different groups, okay? Individually distinct or separate, okay? One of the reasons I want to do this is I still feel that as a group, back to the microphone, that we're trapped in app land, okay? That if you buy into the Apple family, you get everything kind of working, and then you're good luck getting content, good luck getting interaction moving across these different devices. So this is kind of where we are now, this lovely archipelago. Each individual set of islands, quite beautiful, but totally disconnected from one another. Okay? This is discrete, separate. This is discrete. Okay? And this is the type of discreteness that I'm interested in. Okay? Why is this audio all crackling? I can just speak loudly. Better? Maybe I'll speak. Well, okay, at the very back, can you hear me clearly? Wait, there we go. See? And the thing is, if I wasn't happy with the response, I could just add in an extra virtual layer of like super enthusiastic, like woohoo! Because I don't have to live in this reality anymore. This sucks. No. That's why I came to New Zealand, to see the future, because I can just paste in whatever I want. Anyway, so to be discreet means to be careful, to be prudent with one's speech or actions, and to try to keep things confidential and avoiding embarrassment, okay? Now, in that situation, once you knew what I was doing, it looked kind of performative and theatrical. But if it was subtle and you didn't actually know what was going on, I could get all kinds of interactions, not to like fool you, but just to kind of maintain the social connection between us. So that's discrete, this is discrete. Now, the future is already here. I really have always believed this. And it's just not evenly distributed, as William Gibson said. And I think this is a good example. You cannot buy this in New Zealand. It is hard to get these things. The trouble I had to go to get mine, the trouble Mark had to go to get his, the ones we have are on loan from friends in research labs who actually give them to us. They just are difficult to get. So that's not evenly distributed. Certain people have them, certain companies have them, not everybody has them. Let me take this from the device. So let's look at this globe, okay? This is the distribution of where everybody is, okay? Let's just think about where we actually see people being discrete, okay? So when I think myself, my time living in Japan, I think of many characteristics of people trying to stay discrete and be discrete. So when we think of being discrete, we want to be kind of subtle in our interaction. So I think the way geisha interact in a social context is a nice example of being discrete. Kids, not so discrete. Now, when we look at computing, there's this vision called ubicom, okay? Ubiquitous computing. But there are many visions of computing of the future, okay? So I would encourage you, if you're interested in thinking beyond just the graphical or the mobile or the current version, even this thing, even this augmented reality, now you've seen it, you get the idea of it. You know, I could paste everything in this room, and then we could think, wow, that could be interesting for games, for theater, for going to concerts, for like the home, all kinds of potential. Great. That's now, okay? You want to go beyond now. So go to this visionsofcomputing.wiki.cs URL here, and you see lots of other visions. Some are really far out there, okay? It's really, really far out there, and some are in the kind of here and now. Let's have a look at where somebody's other vision, and I definitely need audio for this one. Could I get theoretically get audio? Or not theoretically get audio? So people have been having these types of visions. No, not a chance?
Impossible.
Impossible.
Yeah, you have to change
the
settings on your computer.
Okay. Let's see, is my computer actually making noise?
Apple.
No.
System preferences.
System, oh dear.
Over the Apple. Sound. Yeah, sound. And then display what? That's weird.
Yeah, I think it is because. So that website has vision videos of about 100 of them going back to the 1950s, and I think they're very instructive. Okay, so I've now shown you that. You now know that there is technology that you can buy to America, buy one of these things, bring it home, start developing, start thinking about what you actually do. It knows something about the geometry, not great, not perfect, but then you think, wow, I'm in a medical domain. That's going to be something I can use to like add in extra information in my physical space. Okay, so you can already think about tomorrow, 10 years from now. Okay. At any given moment in time, we're all doing this. We're all thinking about possible tomorrows. But let's go back in time and look at what people thought of the future. What would the future look like? So this is what is referred to as yesterday's tomorrows. If that makes sense. So going back in time, we're looking forward to where we are now. And there's no audio. Okay? This is a shame. Okay? General Motors, and I wanted to play along for too long. General Motors concept video of what does the automotive industry look like in 1976. The key to the future. So basically in this you'll see lots of singing in videos in the 1950s. That's what the 1970s was going to look like. There's going to be lots of singing to explain how things are going to get along. okay? And then like they'd be disappointed because they couldn't get onto the traffic. And then he's like, what's the world going to look like in 1976? And then they jump forward to this highly amusing theatrical version of the future. That's what this display is going to look like. Now you need to look closely, okay? So there are little tiny things that are interesting in this that you can actually see. So they're going along the road, happy days, in their Swede wagon car. There's an autopilot. They get in. This is how autonomous vehicles are going to work in 1976. It's a bit Batman-esque. Okay, they're autopiloting. They're zoning in. Now look out the window as they're zipping by. Look out the window. They've got a tower controller, very very Thunderbirds, tower controller. But look out their window. And now he takes his handle. There's the autonomous vehicle taking over, and he goes sailing by. And if you look out their window as they go sailing by, I hope you actually see what they see is augmented reality content at their window. No, it's gone. Okay. This is me. Oh, this is a different one. This is roll. No, I'm not going to show you that one. Okay. So I would say that I wrote this paper a few years ago. This is where we start getting into stuff that I've actually done. Where we called ubicomp fairyland computing, where we said it was just a badge of convenience. And then we got really harsh and we said this notion of calm computing, where everything's going to be zen and we're just going to walk around like in some sort of placid state, that's nonsense. There's no commercial case for it. Technology needs commercial drivers to make sense. This company, how much has been invested in Magic Leap? $1.7 billion. You're going to have to sell a lot of those things to get back $1.7 billion, okay? There's going to have to be commercial need. There's going to have to be an inflection. There's going to have to be a paradigm shift to say, actually, school children will need it, we'll all need it, and actually, it's not going to look like that. It's going to look like a pair of glasses. It's just going to be part of the fabric, and it's going to be the iPhone of 10 years from now, or something like that, okay? So I would say ubicomp is not a failure, but it's a failure to say that everything that's happened is ubicomp. Because you say, oh, the mobile phone is ubicomp, everything's ubicomp. It's not really. These visions are good for inspiring thinking and action and doing and research, but they're not necessarily the end goal, okay? So discrete computing is exactly like this. I say this as a precursor so that you don't go in 5 years' time like, oh, we didn't have discrete computing, you failed. I'm like, thanks very much, that was nice. No, I say this so that you understand that it's a way for me to think, okay? So it's when you design things to be unobtrusive through design, through development, and through use, okay? But it has all the building blocks. It's pulling in from stuff we've already done. We have all these things on wearable computing, all these things on invisible computing, ambient, ubicomp. All of those things can be woven together to build discrete experiences. But then what is this word discrete? I mean, stereotyping, I would assume most people know this word. You probably don't use this word in your day-to-day vocabulary very often. Synonyms for discrete include to be wary. Okay, that's an interesting way to think about being discrete. Or to keep things confidential. Or don't attract attention. Or to be careful. To be prudent. To be inconspicuous. To avoid embarrassment, or even to be unobtrusive. These are the ways to think about discreteness. When you leave here, if you only have one idea based on one of these, I'm happy. If you have ideas for all 7, I'm even happier, okay? But at least go away hopefully thinking that one of those could be useful. The idea for this came originally from thinking about, well, what does it mean to be wary, okay? That's a feeling of showing caution about possible dangers or problems. So this idea occurred to me, not here, oops, this is showing the wrong. Somebody's trying to share this in here. What the hell? Oh no, did I paste in something in the wrong location? Oh, that's annoying. I've broken my slide somehow. Okay, so I'll just explain where the idea of wariness came from. There's research done by Matt Jones and Ruda Joshi, an international group, where they basically went out to different locations in different environments. They went to care workers in Bangalore, they went to taxi drivers in Cuba, they went to different locations, and they asked people, you know, what are your challenges, what are the issues? And those emergent user groups came back and said, well, I would like to have a mobile phone in my hairbrush. Okay, well, why? And you have to think about that. Now, I asked this question, so why would the domestic workers in Bangalore from Bangalore, excuse me, who are working in Dubai, I should say, the people from Bangalore working in Dubai, why would they want to have their mobile phone in a hairbrush? Any suggestions? So they wouldn't be taken, so they'd be worried about the technology being identified as something valuable and getting stolen from them. That's part of it. Anything else? So they can talk while they're working. because their employers were getting very angry. And you read the research paper, I'm not going to say what they say in the paper, but what the employers were doing to these workers is not good. Okay? You find somebody's talking on their phone and the employers react badly. The Cubans wanted their phones to camouflage themselves, and the people in Nairobi wanted something else. So they were wary about their technology. It's valuable, it's sensitive, it's showing that they're not doing their primary task, they're doing something else. So they were wary of their technology. So as soon as I read this, I thought, that's an example of discrete computing. They want their technology to sort of blend into the environment so they don't get into trouble. But they also sometimes want information to be kept secret, okay? We sometimes want information to be kept secret so only we can see it. Now with this headset, if you couldn't tell I was wearing one, you might not know, but that's not commonplace yet. So let's have a look at another system that we did a few years ago. This is called distance-based dual views. Two things happening here. It knows how far your eyes are from the screen, so it changes the size of the content. The font gets bigger, the font gets smaller. But also it knows where you're sitting, okay? So on the right, you see subtitles. You move your body from the right to the left, you don't see subtitles. Okay? We don't change the display. Both points of view see this. As you move around, watch, the subtitle appears. So on one side, we could project in English, and the other side, we could project in a different language, okay? Off of one display. Okay? Both are happening simultaneously. You think, well, how is that possible? That's not the impressive thing here. That's just like the one little research project that I did in a university a few years ago. What's impressive here is that people have scaled this up. There's a company now called Misapplied Sciences that basically want to have a display that 10,000 people can see simultaneously. That means in a lecture room like this, in the future, you can all see slightly different versions of the same screen. Subtitles, surtitles, extra content, translations, extra information that means something to you but nothing to anybody else. Okay? That picture is hard to understand. Okay? What you're actually seeing there is there's a big screen here facing that way. There's a photographer here facing this way, and there are a set of mirrors. He takes a photograph of the mirrors. The light has come from the screen behind him, bounced onto the mirrors, and then come into the lens of his camera. And that one screen is showing all of those individual displays simultaneously. Okay? That technology is called parallel reality pixels. Okay? So that's the kind of future you could be thinking of. Okay? So you think now every public display can actually go out to many people. Concerts, stadiums, public displays. They don't have to go to one point, or everyone has to see the same thing. You can have a multitude of points coming off of one thing. And they're working on commercializing this right now. This is at least 10 years away, okay? Unless they get a huge injection of cash. Even 1.7 billion probably wouldn't do it for them. It's going to take a long time to actually kind of ramp that up. So one of the things we've done in the past is a system called Multify. And I can actually hold two devices up and go, there's one display, there's another display. These are two totally separate islands in my archipelago. This is Apple Land, this is Magic Leap Land. These things are not easily going to talk to each other anytime soon, okay? But what I know is that if my eyes are looking at that display, two pieces of information are being overlaid. And maybe I don't want that. Maybe I actually want them to be coordinated. And that's what we did in Multify. So in Multify, you'd see some of the content in your head down to display, and you see some of it in your hand. The piece in your hand would be high fidelity. The piece in your eyes would be low fidelity. It stitches these together to kind of minimize the seams to actually give you an extended space. So the simple idea would be if I was using glasses like this and I bring up a map, suddenly I'd see the map and I would just shake it. And then the entire floor would be filled with the map around me. Okay, so I have a map here and I'm like, so we're trying to navigate it. So I can just have some gesture and suddenly the entire floor would have the map. And I'd be looking over here and then myself and Mark would say, okay, we'll run here, go over here and over here. Say, what is that suburb? And I just use my phone, like a lens, to look at the content and go, oh, right, okay, I don't see the name of that. In the low fidelity version, you might not be able to read the name of the town. Another bit over here, you go, what is that? And you can zoom in on a shop. And you look inside of it and you go, oh, very interesting. Okay, so use this as a lens. Okay? But that's one way. This magic people is one metaphor. There are many ones. So this is kind of what it looks like inside of Multify. Okay? You type on the handheld device, and you see the output in your eyes on your head mount as well. And what we have to do is we have to keep the two stitched together. And when I was talking about there being fish over there, and there being a Tyrannosaurus Rex over here, and a Tyrannosaurus Rex there, and it's sort of wandering across the desk, it's because the system was able to track and scan the room incredibly accurately and knew that there was a surface there with an edge to keep the Tyrannosaurus Rex in line. What's also fun which actually I should have done, but I didn't do, is that this actually also knows its location. So when I have the Tyrannosaurus Rex and it knows about the geometry and sitting there, like, sorry, I can whack it and it falls off onto the ground, very grumpy, and then starts wandering around. Because it knows there's a surface there, it knows there's a surface there, it knows what this thing is, and bang, off it goes. So this is the kind of multi-device interaction that you can actually have when these things know about each other. Why do we do this? Well, it takes time to get these things out, you know? Access cost, there's my mobile phone. There we go, it takes time. Or interacting with these wearables, they can become kind of small surface displays. They're not very big, okay? Or if they're head-mounted display things, they're a bit of a nightmare to kind of interact with as well. So this kind of like Google Glass. So they're fiddly. So why just use that? Like you've got this huge surface. Use this with that, and then together you get a better experience. The multi-fidelity, okay? And there's the typing again, okay? You also get all kinds of interesting, we wrote a journal paper on this for the Mobile User Experience Journal. There's about 16 different aspects of this that fall apart when you actually start thinking about this. The visual depth, the visual fidelity, the social exclusion, all kinds of things kick in when you actually start doing these kind of multi-display stitched environments. And you also get the alignment modes, which is one of my favorites. So who's in control? Like, is it my body's in control, or is the device in control? So in the Magic Leap setup, my body's in control, okay? I do this, I'm talking to you, there's no content here, we're just having an interaction. Until I turn left and, you know, kind of start getting rooted or something. That means something else in that, sorry. Okay, anyway. Okay, so the dinosaurs are over here, I can't see them, okay? Because my body is like, it's the central point. But, and then this, in that case, this would basically become a magic lens. I'd go over and I'd look inside the dinosaur, etc., all happy. That's one way. I could also make it the device-centric way, which is I look at the device, that's the world. And if I then flatten this down, the map falls with it. Because everything is glued to the device. My tablet, my phone, my laptop, my whatever it is. I move it around, all the content goes with it. This is the referent, not my body. Different ways of thinking about it. Okay? Your body becomes incredibly important in these spaces, but so too the devices that you actually work on. Sometimes in discrete computing, you don't want to attract attention. You really are trying to do it in a way that you're not becoming a performer. You know, you're not a monkey on a string. You really want to do it in a way that's pretty subtle. So you want to weave it in so it's pretty seamless. This is an example of a concept that's very commonly studied in psychology called change blindness. What we want to do here is three different things. We want to take advantage of the fact that we know the proximity between your face and the display, and we want to change things. Because we know at great distance you can't see certain content, and up close maybe you can't see things. And we want to manipulate that and to add and remove things. So the idea would be, and I'm sure you've all had this kind of experience, you're trying to navigate through a city, and you get like your Google Maps view, and it's showing you this highly detailed map, but you can't necessarily read it so easily. So what you maybe just want is an arrow, which says go that way. So at a distance, you have an arrow, you just turn it, just says that. If you want more details, you bring it closer. You bring it close enough, suddenly it transitions into a map. You bring it really close, you get street level detail. Now let's play, something's beeping. Arm extended, up to close. Now this is the proximity that's being measured, changing proximity, and adapting the interface accordingly. Okay? I'm losing my crowd here, what's going on? So one of the questions there is there a change detected between A and B, and there's a change detection between these two states here? Okay, so here you're seeing change blindness in operation. So look at that image. There's image 1, there's a change, and then there's image 2. The change is being detected in your brain. Okay, if you see the change, it's in your brain. Okay, can anybody not see, and is willing to admit in public and be vaguely shamed, can anybody not see the change on screen? The further back you are, the harder it might necessarily be. You can't see it? Yeah. Oh God, it's not playing. Oh, there it is. Okay. So the reason you couldn't see it is because you're very far back, so the angular distance is quite tight, and it's not going above what's called a flicker threshold that you can actually notice it. Don't feel bad. Everyone else is about to feel equally bad in a moment. Okay. Let's try it again. What we're going to do is we're going to add in one extra thing, which is a flicker in between. And I'll give it, let's say, 10 seconds. And then we'll just do a show of hands. And please be honest. Like, if you can't see it, you can't see it. It shouldn't be surprising. Okay, so 10 seconds, next image. So hands up who can see the change. Not so many. Look at the plane. Look at the engine under the plane. Oh, you tricked me, you tricker, you. Of course I didn't trick you. This is a well understood phenomena. We can piggyback on that phenomena and do things with it for the benefit of the user, not to trick them. So what's happening here is you've got proximity, the distance, you've got the interface adaptation, we're going to change the interface, and thirdly, we're going to take advantage of this changed blindness. That's only one type of blindness. There's inattention blindness, there's lots and lots of other ones that can also be taken advantage of. So let's have a look at this one now. Something's changing, so watch, either on the left or on the right. We play it twice to see whether or not you can see the change. Okay? Let's say now hands up. Who saw the change? A few people, okay? Watch again, and watch the 20th Street area. You'll see it circled in red in a moment. Most change blindness experiments only do the change once. We do it twice, so you get double the opportunity to see it. So now they move the iPad away, and suddenly this piece of information, the green region, just fades away. Disappears, and then they bring it back towards their face, and it reappears. So we do that. Test experiment. Did you see a change? Yes, no. Did you see a change? Yes, no. Again and again and again and again and again. Small things, smaller things, bigger things, really big things, really, really big things. And we try to understand what's going on. Is it the motion of the device? Is it the scale? What's actually happening? So the results show that with gradual change, 60–70% of people don't see it. It drops down with other types of change. That's interesting to us because that's an opportunity to do something in the interface, add and remove content without people necessarily noticing. So basically the interface could suddenly add in labels that you didn't see, and you're not going to be like, they're going to be like pop-up ads. Okay? We also built a system called diff displays. What this was looking at was your face and basically figuring out which of a multi-monitor system you're actually looking at. Okay? So you're looking at one display, and then the displays you're not looking at are basically frozen. And when you look back at them, you get a very simple visualization to say, in the time you weren't looking at me, this is what happened. Okay? What's interesting here is the types of visualizations. So like, you can change the color display, you can put in a little pulsing aura, you can change color, you can do all kinds of subtle changes here to actually understand how the interface is, how you're supposed to notify people of change. So within diff displays, we had a control condition, which was how many people were changing their view, and then in other cases, what was actually happening with these other types of visualizations. And we dropped down the number of changes quite dramatically. Okay? So sometimes in these systems, you also want to be careful. Okay? There's another way to think about it. So to be careful is to do something with thought or show attention to care. Okay? So in this system, we basically want to study what happens when we have these multi-display environments at scale, like big things. You know, you've got two devices at work. You've got a triple head monitor. You're in some sort of command and control system. That thing on the left over there, on the right over there, that's the UAV control system for drone control pilots. Every time they get a new sensor, every time they get a new feed, every time they get a new bit of data, their solution to the interface design question is stick in another screen. Okay? This is not smart, okay? For lots of other reasons, okay? But we wanted to study what's actually happening when you're trying to attend to all these different things simultaneously. And the thing in the middle is actually an IBM product that they sell in Brazil for doing city scale monitoring. What we want to do is do the change, so do the eye detection, and then embed this knowledge inside of the user interface widgets. So widgets are these things that, widgets are things which are used in programs to basically build interfaces. And now the widgets themselves know, have you been looking at the screen that I'm on or not? And in which case, buffer the information. So when you do look at me, I'm going to tell you that something's actually changed. So there's opportunity here. I'm going to skip over this. These are the kind of widgets that we're talking about. So it's literally just a C# widget library that now understands the fact that you are or are not attending to the display. All we're doing is just manipulating a very small component within that space. We then did an application in the health domain, and we then studied what was actually happening over long periods of time with care practitioners to see were they actually seeing more or less with our notifications. And what you can see here is that in remember my colors here. In blue is with our toolkit, and in red is without our toolkit, without the toolkit. So you can see for many of the tasks, 3 of the tasks, 1, 3, and 4, they were missing 80% of the notifications. They just weren't seeing them because it was over there, and they were looking over here, and they look back, and oh, nothing's changed. You're like, the patient has fallen over, and you just missed the notification. Now, why do you think we are as good in task 2 as they are in task 2? Okay. Why? Yeah?
It's
No, this task was actually spread across multiple screens. There's a different reason. Okay, so let's think, so the sound. So basically the designers of the interface knew that this was such an important thing that you don't want to miss. They've engineered in special notifications to say we don't want to let people miss this. Okay? But they only did that for one of the 4 tasks. They didn't do that for all the tasks. They ignored the other ones and they just said, oh, I'm sure people will see them. And they didn't. Okay? Now they don't have to worry. It's just built into the toolkit. They get it for free. Sometimes when we're being discrete, we want to be prudent. How much longer do I have? 20 minutes. Okay, I'm going to just set a timer. Because we're getting towards some interesting new types of sensing at the end of this talk. I've never actually done the magic leap bit of this talk before, so I just didn't know how much time that actually took up. Care, thought for the future. Okay, so we have a system called Spider Eyes. And what Spider Eyes is actually doing is you're not using computer screen mouse, you're just using a big public display and you're using your body, but also you're using the fact that you're working as an individual, as a group, to manipulate and control what you actually would see in the large screen. So if you move as a group, you get a group interaction. You move as individuals, you get individual interactions. And it is tricky, you know, say like how do you split a screen that you're trying to share with multiple people? You know, maybe one person should have the whole screen and other people should have like a portal into that screen. And this is the kind of thing you have to think about if you're doing game design. So here you see a person comes in and suddenly it actually senses that they're looking, so they interact, okay? As they're interacting, you can imagine this is a public space, this is a lab, this is all kinds of different things. Somebody else comes into the environment, eventually. There we go. And they're not paying attention. You're not paying attention to me, I'm not paying attention to you. They ignore them, okay? Sometimes we want to be inconspicuous when we're being discrete. Not visible or not attracting attention. Okay, let's play a game, which I always play when I come to different countries. How many people own, this is a mobile phone, how many people own or regularly use a mobile phone? Yep. How many people, when they're in a social situation like a bar or a pub or dinner, keep their phone in their pocket? Okay. Few. How many people take it out and put it on the table? Okay. How many people put it face up? How many people put it face down? Okay, so again, when you're using your phone, how many people occasionally put it face down on the table? Hands up. Hi. I have a lovely product I'd like to sell you. You are my users. This is the use case we're looking at. To be discrete. Okay, because you can't see the screen. You can't see the screen, but the screen can see something. And if the screen can see something, we can see something. Okay? So we invented a technique called spec cam. Okay, so what spec cam does is it basically flashes the screen through a multispectral light source pattern. You see it there, flashing the colors. The light then bounces back from the screen into the camera, is seen, and then we train based on that. We extract all kinds of features. All we're doing here is we're sampling. We're saying, here's a bit of paper, here's a different bit of paper, here's a plate, here's a ceramic, a porcelain plate. Sample, 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 sample. We're just learning the environment. We don't actually have to tell you to do this. You just put the phone down. The system will go, oh, I've never seen this before. I better sample it. And then after you take it up, it will go, hey, you put me on something new. Can you tell me what it is? You go, oh, that's the bedside locker. Oh, that's the kitchen table. Oh, blah, blah, blah. And after you've done a few things, you're done. So here you go. You sample everything that you need to sample. Okay? So what could you use this for? Well, now you could have music control. So all the places in your home, every time you put it down, Spotify could fire up something different. Inside the bed, in the kitchen, everything you want. You could also have it so it could do reminders. It could actually know where it is and know what you actually mean by that. You're in a restaurant, you move it from the napkin to the table or like move it around. Just moving it to different places actually will trigger actions. That's what it looks like. We get data out of it. I'll explain in a second what we actually do with that data. But basically what's happening is you place the phone on the surface, the light comes out, data comes back, you do what's called feature extraction and labeling. You use that to build a machine learning training process, which I'll explain, and you build a classifier. Now the classifier just understands the data. Okay? And there's lots of different classifiers in AI that we can use. In this case, we were using random forest, and somebody asked recently, could you use deep learning? Yes. Bit heavyweight, we don't really need it. We use a random forest. I'll explain what that is. Then you can basically feed the features back in again, and then out would come the result. So basically all you then have is, oh, you're on the porcelain plate. You then, as an application designer, have to do something with that. Like, you're not going to tell people like, oh, it's a porcelain plate. Like, that's not the point. The point is, you can tell the difference between different things. We did an experiment, because we always experiment on these things. We compared this to a spectrometer. Spectrometers are designed for exactly this, for picking up color. And we did better, which was very surprising to us. Okay, we thought, let's do it at least as well as the $10,000 spectrometer. But we did better. We did better because our light source is so much bigger. The spectrometer is a point source of light. We have a much bigger surface. So we're looking at a much larger area. All the contours of the surface. All of the individual characteristics. And you think, there's not enough characteristics in there to actually tell the difference. Oh, I beg to differ. I know I beg to differ because there's a company in Edinburgh that is now creating a type of GPS which is based on having a camera looking down from the bottom of your car. And as it's driving along, photograph, 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 it looks up in a database going, oh, have I seen this photograph before? Oh yeah, I know where you are. You're in Auckland. Oh, I know exactly where you are, down to a millimeter. And thinking, why just not use GPS? Well, the Americans might shut off GPS for a start, or it could be very expensive, or you might be driving underground, like in a mine, for example. So now what you have to do is just drive the car around, take all kinds of photos of the ground, lots of them obviously, and then just match them. Okay? We're doing something similar on a much cheaper, lower scale, just using commodity devices. Our results, where there's a big black line up the middle, and there's nothing off the edge, it means we're not getting confused. And that's a tough experiment, okay? That's a tough thing. We're showing you a ceramic plate and a porcelain plate, and we're saying there's enough differentiable features in the color spectrum space that you actually pull those two things apart. Then we actually move on to a system called RadarCat. This is using a similar approach, but isn't actually using computer vision, and that's very important, okay? This is, if I could only emphasize one thing about RadarCat is, RadarCat does not see like we see. Okay? RadarCat is seeing a different part of the electromagnetic spectrum. It's seeing radar signal. Okay? We can't see radar. Our eyes can see the visible light. We cannot see radar, but RadarCat can see radar. Okay? Same pipeline, exactly the same pipeline, but now it's using different types of data. What's important for me in this type of work is that we involve lots of our undergraduates. So many of the papers we've published recently have involved first years, second years. We get them involved in the research publications early on. This is a chip. It's called a frequency modulated continuous wave. It's monostatic, means everything's built into the same baseboard. 2 transmitting, 4 receiving elements for a simultaneous operation of up to 8 channels. It looks like this. It has a little weird logo on it. It's about the size of a coin, a little bit smaller, and it's for sensing. It's not for sensing the way we used it. It's for sensing something else. It comes in this kind of little package. The chip's in there. This is what it's designed for. Okay? So when Google invented this, they spent 50 million on the investment of this thing. They invented it for this. They want to be able to gesture at a distance. Okay? So you see, with this, when I'm interacting with this, it has cameras. So I can do certain gestures, okay, in front of it, like a hand, an open hand. Like a minimal set of gestures it will understand. But typically, I'm using a controller. Okay? With the Google Solly, you don't need that. You have your whole set of hands. And now, all of these things that I've just rendered. So over here was the Tyrannosaurus Rex. And Tyrannosaurus Rex, I can look up to and get close, and you can open up his palm, and there's a button there, or like a little dial. And I can twist the dial, and then he becomes really big, right in front of me. Okay? Because I can sense that with this type of sensing. This is not in the view. So you have to then think about fusing all these things together if you want to advance the field. So this is just basically picking up the data and then allowing you to do these different types of gestures. Okay? A little virtual button, a virtual dial, a little slider, a little trackpad. Okay? When we showed the work, this is what other people were doing. Gestures, gestures, gestures. Lots of gestures. Apart from us. We did object recognition. We were able to use it to identify things that were in proximity. And since then, we've done much bigger distances. Okay? Object recognition. The students were picked. They were flown out to San Francisco. They were able to show the work. And we're now in the process of patenting it, actually doing lots of different activities with it. So what does it actually look like? Well, basically, you put down the objects, you train. Hello, here's the object, here's the object. You have to see it. And after that, you can then reclassify. Okay, you can retest. Water versus, they're different. Versus milk, they're all different. Okay. Here we go, water. This is just the explanation of like what's going on. There's a chip, it's emitting energy. It's a very complicated signal that you get back, very noisy, and then you have to basically do a machine learning step. I obfuscate exactly what's going on there because the patent is still in the process of being filed. Okay, so that's a signal. It's sort of like fuzzy because it's the gesture. But the important thing is, as soon as you put something on it, it stabilizes like that. Now we know it's a pattern. We see it again, we see it again, we see it again. We can train, we can recognize. The pattern is different from the front of an object and the back of an object. Okay? Which means we can do experiments. 26 household objects, 17 different plastics, and 11 different body parts. Okay? Now, what did I say that was an essential part of this type of sensing? What is it not doing? Vision. It's not doing vision. So, how can it tell the difference between red and green plastic? Function. Something's happening in the radar signal. But the pigment, you're saying the pigment. So what do you mean by pigment? Do you mean the color of the pigment, or there's something in the pigment? It's actually being explored. It's actually changing the rotation of the radar signal, is what it's doing. It's actually changing the speed of the rotation. The different dyes are changing the speed of the rotation. So it's a very subtle thing that it's actually doing. Here's the confusion matrix for the household objects. Anything off axis, bad. Anything black on axis, good. Okay? So things do get confused. Okay? It's not perfect. For example, then we do body parts. Okay? So let's let the body part one play. At the very beginning, it starts to play the very simple example of, I'm in Scotland, I'm wearing gloves, I'm holding the phone. So I'm not wearing gloves, and I move my phone over to the hand, and the interface changes. The buttons get bigger because you know you're not going to be as dexterous. Okay? So now we know what your hand you're holding in and what's in proximity to it and where you're placing it. I can tell you I need this when I go out running. The other night when I left, oh, also, by the way, you might want to tell your crew captains on those boats, the distance from Birkenhead to Devonport is not a 40-minute run. It's a half marathon distance that I got to enjoy and experience. And your tickets are made of paper. And when you put paper inside of one of these things on your shoulder, it doesn't look like a single ticket by the time you get to the end of a 3-hour run. Okay? Mashed up into nothingness. Okay? But I'd like my phone to know it's on my shoulder. Okay? I'd like to know it's on my shoulder so it doesn't react as if it's up against my face. Just know it's there and don't act the same as if it's in front of my face. Because it's always shutting itself off. I accidentally touch it, I activate it, and then it looks like I'm freaking it out by touching 50 buttons. Know it's in my pocket, know it's on my shoulder, know it's on the table, and do something smart accordingly. We got a lot of media attention on this one when it was released, okay? I speculate that because when the timing, it happened, it was launched on the 6th of November, or 5th of November, when was it? Basically, in that video, we predicted orange, and the next day, President Trump won. And so people thought, wow, you guys predicted the outcome of the election. You're like, no, we definitely didn't. Some of the videos have been seen millions of times, futurisms 1.7 million times, because people could think of like a million different applications for this, getting rid of barcodes, new ways of interacting with devices and objects. So let me show you an example of what we've done since. We just published this as a journal paper in the last month. This is called Solly interaction. Okay, so now. Hopefully it can play and I can explain. So now we could recognize objects like stacked Lego. We can recognize stacks of other types of things, phones, distances, where you're touching it with respect to your fingers. I hope it's going to jump onto the counting one in a second. Plastics, the locations of the device, everything else being classified. Okay, jump on. Different games you can then build with all of this. So we have the casino industry interested in this. We have the people who are designing new types of interactions. Okay, counting. So let's watch counting. Okay, this is a video. I'm pulling off a card at a time, one by one. Okay, watch that video the whole time as it jumps up to the bottom, up to the top left. As it's playing, you'll see it's keep on going down. Now I'm going to take a sand counter, and it's going to be able to tell how much sand is in there, classified as according to particular levels. Okay, and then that plays. And then we count other things. Sheets of paper, maybe not the most exciting thing in the world. And then finally, actually I'm doing a voiceover here, that's why I'm okay. And then these kind of chips, so you can imagine this kind of casino scenario. So suddenly actually all the individual things in your house all become elements of interaction with the computation. Okay? So right now, you want to tell the computer something, you have to like type in a number. Now, give it a stack, give it a stack. Take something away, take something away. And you saw the cards, the whole time I was taking one away, that's a very fine amount of information that you're actually getting. You can even put down multiple credit cards for paying bills. Okay, again, this got released, a lot of media interest. Always, of course, when you have these things get released, the media completely, not always, but occasionally misunderstands what you're talking about. We were not trying to say the Minority Report was on the way in. That's not happening for many reasons, if nothing for the fact that your upper arms are not going to be designed for holding that weight for prolonged periods of time. What it is useful for is gaming, for example. So casino gaming or children's gaming, because now suddenly all the things you touch and play with now are part of the computational interaction. So if you have something like this and you have Lego, you start building something and then the whole thing can explode. You can have like 50 times the amount of Lego off of one thing. Okay? Two last things. Sometimes we want to avoid embarrassment and sometimes we want to be unobtrusive. I should have said at the very beginning that the idea of being discreet is in the eye of the beholder. Okay? You are looking at me. Okay? Now, I hope I've at least offended each one of you in some way, small, tonight. So you'd say, he's not 100%, he's been indiscreet. Okay? So you have to then say, like, it's for you to decide who is discreet and who's not discreet. I precursor this because I'm about to show you something that some of you might find offensive. Okay. Avoiding embarrassment. So we invented a technique called itchy nose. It's with some of the collaborators that Mark was working with. And again, it's just an example of being discreet. So with the glasses, we can actually detect when you're touching your nose. So we can detect whether you're flicking, whether or not you're pointing or rubbing. And with that, you can then do different types of interactions. So we'll let the video play. This is Zhu Yang, one of our co-authors from KAIST. And he's now going to demonstrate the different types of gestures that can actually be detected with a system called Jin's Meme. It's a type of glass that you can actually get in Japan, typically used for eye tracking, but here we're repurposing it for doing something else. Flick to the right, flick to the left, push, push, rub. He's a good PhD student, he's not a good actor. Okay? For example. This is what I mean by being discreet is in the eye of the beholder. Okay? You get it? Get the idea? Okay. Now you think you're sitting there going, I never touch my nose. I never touch my nose. You touch your nose all the time. It's a huge source of disease transmission in the medical industry. Touching your face is a big, big problem. Now we know you're touching your nose, and we say, well, hang on a second, you've touched your nose. You shouldn't now be touching your hands with anything else. So that's actually quite a useful thing. Not recommended, okay? This got picked up by the Canadian television channel, the Discovery Channel. So here they were explaining, like, you know, here he is, like tap, 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 tap. And then they go through and actually talk about it. It was actually funny, like when these things get released and the media picks them up and then the public starts talking about them, the use case for this that came out was we were thinking of like navigation and like I want to be basically cycling along and just like touching and doing sort of discrete things that other people can't see. Mostly so I can maintain eye contact with you and I can actually be interacting with you. And of course, as soon as it gets out there, people say, oh my God, this is great. I can go to a nightclub and I can just use Tinder, swipe left, swipe right. Like, now, if you're the only one in the nightclub that has this, you can be discreet. If everyone else has it, I think the level of discreetness kind of goes down quite quickly. At the very end, he decides this is how he's going to check email in the future. We don't recommend, okay? So finally, sometimes you want to be unobtrusive in what you're doing. So to be unobtrusive is to be not conspicuous or to attract attention. So here, part of our work is to model the eye, okay? Because when you run a spell checker on what you do, you run a grammar checker on what you do, you run a compiler and you debug the code that you generate. You can check programmatically lots of things. But what you can rarely do is look through somebody else's eyes. And the reason I show this is because I want to actually redo this work with respect to this device. You see how I had to struggle to try and get you to get the appreciation of, you know, the 50 different versions of me. And that's going to be fun, isn't it? Like I'll have the young version of me running ahead, the slightly middle-aged version of me, the overweight version of me, all these people, like, you know, I'll be trapped in like middle-aged land with like 40 versions of me all running 50 different directions, okay? But what I do want to know is I want to know, what do you see? So to know that, I want to model the eye, okay? I want to build a model of the eye so that I can look through that model at the real world. Looking at displays, looking at fonts, looking at information, looking at the Tyrannosaurus Rex, looking at things without actually using a real human to look at it. Okay? And then I can use simulated eyes and then look at those things. Sometimes the solution is, make the font bigger, just make it more legible. That's nonsense, okay? You're talking, like, if I literally fill this place with, like, you know, Tyrannosaurus Rex and all kinds of stuff, and then I have labels, like, if everything's going to be like a 100-point font, it's going to just be a train wreck. Like, it's not going to be a usable space. Okay, so you need to think differently. So what we do here is we take information from optometry, we use it to build models, and we use that to make predictions, and then we adapt the interface, and then we change things accordingly. It's a very low-level vision of model, very low-level model of vision that you're actually talking about here. So what you're saying is, like, how much blur is going on in the eye. Okay, this is what's actually happening inside of the lens. The rays come in, they go pass through. There's a little dotted line, which is ideally what we would have happen. But in reality, our eyes are all doing slightly different things. You know, some people have short-sightedness, long-sightedness. Some people have astigmatism. Some people have blur, defocus. Some people might be actually getting macular degenerative diseases. Some people might have other issues. So there's lots of eyes. There's understandings of populations. And that's actually my time. So I'm actually just basically done. We basically built a predictor based on this. Over here, let's go for, can anybody see a pattern in there, or does it just look like a big blob of grey? Big blob of grey.
No, there's a few lines.
Few lines, okay, you've got good eyesight. Okay, what about just there? Okay, blur or a couple of lines? Okay, so at the very back, blur, blur. There you go. That's what we want. We want the distance and the predictor and actually to tell us that things lose visual detail. But most importantly in this, no matter where you are in the room, right at the back, in the middle, what letter is that? C. It hasn't lost that. It still retains that information. You still can tell it's C. This pattern, gone. Okay? So the detail has been lost because of the blur. So that's our way to categorize information, which means we can do this. We can look at eye charts, simulated eyes. We simulate 3,600 pairs of eyes, all based on an understanding of optometry, a human population. And then we use that to look at those eye charts and then say, this is what our model is telling us. This is what is legible and illegible in these things. And it lines up perfectly, nearly perfectly, with what actually happens in clinical practice.